Okay, so the average length of short hospital stays for men is slightly longer than that for women, 5.6 days versus 4.5 days. That's based on this sample. Our random sample of recent hospital stays for both men and women revealed the following. The goal of the study is to determine if there is sufficient evidence to conclude at alpha equals 0.01 that the average hospital stay for men is longer than the average hospital stay for women. Okay, so this is a two-sample test. Let's see what we have here. So step one, as usual, is null and alternative. So for two-sample tests, the null hypothesis would be that the first mean is the same as the second mean. The first population mean is the same as the second population mean. Or another way you can put this is the first mean minus the second mean is 0. If they're equal, when you subtract them, you have to get 0, right? The alternative hypothesis here is we're trying to determine if the average hospital stay for men, M1, is longer than the average hospital stay for women, mu2. So the hospital stay for men is longer than the hospital stay for women. Or, put another way, mu1 minus mu2 is greater than 0. If mu1 is greater than mu2, if I subtract mu2 from mu1, I should get a number that's larger than 0. Like think about 5 and 3. 5 minus 3 is 2, which is bigger than 0. Null and alternative hypotheses. Step 2 is to determine the critical value. So let's do that. I think we should check our formula sheet and see if that gives us any insight here. This is chapter 9. How do I know it's chapter 9? Testing the difference between two means, two proportions, and two variances. Yeah? Okay. So the z-test for two means is independent samples. There's our z-test. Doesn't say anything about, wait, is this a z or a t? We have the population standard deviation, so this is going to be a z-test. So I'm kind of fooling myself because I didn't even need to do all of that. Step 2 is that the critical value. Now this is a greater than, mu1 is greater than mu2, so that's a right tail test. Right, one tail to the right. I want to determine this critical value. This alpha here should be 0.01. So let's go to our formula sheet. 0.01 right tail test. Go down to the t-distribution. One-tailed, 0.01. That z-test value, that z-critical value is 2.326 or 2.33. So this z-value here is 2.33. That's the answer. 2.33, or unrounded from the table, is 2.326. That's our critical value. Just one of them. Okay, question 18. Which of the following will be classified as dependent samples? So I think I need to define independent and dependent samples. Okay, so in independent samples, the subjects selected, we're talking about two samples here, right? The subjects selected for the first sample have no effect. I don't know, I'm blending words together. Have no effect on the subjects selected for the second sample. And for dependent samples, the subjects selected for the first sample do have an effect. Do have an effect on the subjects selected for the second sample. Okay? So let's go through each of these and kind of try to make sense out of it. So which of the following ones are dependent is what we're asking. So the weights of identical twins, right? So imagine if I'm picking subjects for this particular study, for this kind of for this sampling, right? So I have a bunch of children that I'm choosing from, right? I've got a pool of children that I'm choosing from, and I choose one child, right? I choose one child, and I go back into the pool to select the other child, the second child in that particular sample. Can I choose any of the children, or am I restricted on who I can choose? I'll draw a little picture. So there's my pool, right? So let's say I go in and I choose this child. Can I go back in and choose any other child? No, I'm restricted. I have to choose this child because I'm comparing the weights of identical twins. So when I choose this one child, I'm restricted for the next child that I choose. The subjects that I select for the first sample definitely has an effect on which subject I choose for the second sample. I have to choose this second child because I'm looking at identical twins. So this is dependent. Okay. So if I'm looking at 2, effects of a drug on tumor size of 2 different groups of people measured by a before and after test. Same kind of idea. I'm doing a before and after test. Doesn't that mean I test one person and then I have to test them again? Because I have to test them before they take the medication, and then I have to test that same person after they take the medication. Even though I'm choosing from 2 groups of people, once I choose that first subject, I've got to use that subject again. If I have to use the subject again, if I do a before and after kind of situation, that's dependent. Or even if I have a pairing, if we're talking about being matched, dependent. Here we go. The effectiveness of 2 different brands of antacid on 2 different groups of people. You see how I'm testing 2 different brands of antacid and 2 different groups of people? That's independent all the way. That's independent all the way. 2 different training programs on 2 different groups of individuals, that's independent all the way. But here, test scores of the same students, repeated, I'm using the same student. So when I choose a student for statistics, I have to look at that same student again for art. Because I'm choosing the same student and I'm looking at the same student twice, that's dependent. If I choose student C here for statistics, I have to choose student C again for art. So 1, 2, 5 are dependent.